Hey, my name is Rigvid Goyal, and this is my Lab 4 report. This lab involves application of principles like the conservation of current, which is called the node rule, and the conservation of energy, known as the loop rule, in virtual circuits to predict and evaluate measurements like voltage, current, and resistance. This lab also involves observation of how capacitors are charged and discharged and how they affect current within a circuit. For the first part of this experiment, I used a circuit that I made virtually that was modeled similarly to the picture that I've used on the right. With two 1.5 volt batteries supplying a current through a 47 ohm and a 100 ohm resistor, I predicted that the current would be 0.02 amps. And that is the measurement that I got from both of the ammeters. When one of the ammeters is replaced with a voltmeter, the voltmeter reads -3 volts. Since the voltage difference of the circuit and the voltage difference of the battery have to equal 0, and the voltage of the battery is 3 volts. The ammeter reads 0 since the voltmeter is attached in series and adds a large resistance to the circuit. Now here on the bottom right, there's a picture with the different segments of the circuit, which I measured using the voltmeter. And here are some measurements I got. In AB, it was 3 volts. For BC, it was 0 volts. For CD, it was negative 0.959 volts. DE was 0. EF was negative 2.041. And FG through HA was also 0. When you add up all of these segments, you find that the net potential difference adds up to 0, which checks out with the loop rule, which we also employed earlier. Adding the voltmeter attaches a high resistance branch in parallel, which does not significantly alter the total resistance or current of the circuit at any point. In contrast, adding an ammeter in parallel increases the current from 0.02 amps to 0.06 amps because the ammeter has a very low resistance, and adding a low resistance object in parallel significantly decreases the total resistance of the circuit. And here are some calculations that I made using the numbers that we got from the virtual circuit. They're all similar to how I labeled them in the virtual circuit, which was that the 47 ohm resistor calculated to approximately 47 ohms, the 100 ohm resistor calculated to about 100 ohms, and the wire and ammeter in this virtual ideal circuit both came out to 0 ohms. Here's some more data and observations. I set up the circuit slightly differently. When a 10 ohm light bulb, a 9 volt battery, and a 200 millifarad capacitor are attached in series, the bulb lights up temporarily, but eventually stops shining. When the battery is then disconnected, the bulb once again lights up, but then eventually stops shining. When the battery was attached, the capacitor became charged and the current was flowing from the positive end to the negative end of the battery. After detaching the battery, however, I realized that the current created by the capacitor makes the current go in the opposite direction. The capacitor with a 10 ohm light bulb had a charging time, at least visually, of about 2 seconds, and has a discharge time of 10 seconds. When I replaced the 10 ohm light bulb with a 20 ohm light bulb, I found that the charging time increased to about 5 seconds and the discharge time increased to about 20 seconds, so both measures about doubled from their 10 ohm counterpart. When I repeated this experiment with a 30 ohm light bulb, I incrementally measured time and voltage across the capacitor and got the following results. And here I have some key value pairs. For 5 seconds, the voltage difference came out to around 3.711. At 10 seconds, it was approximately 1.711. At 15 seconds, it was 0.754. And finally, at 20 seconds, I got 0.346. I took these values and plugged them into this formula right here, which relates voltage, time, and the time constant. When I plugged in these values and calculated time constant for each one, each calculation brought the time constant to around 6, which makes sense since resistance times the capacitor value is 30 times 0.2, which comes out to about 6. And here is a graphed chart of the key value pairs that I calculated earlier with voltage and time. On the bottom, you have seconds that go by, and on the left, you have delta V. Finally, some questions. What if you were to do this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked up to it? In real life, the ammeter would have some resistance, whereas in this computational model, there was no resistance, which would have slightly lowered the current readings that I got in this lab. The slight resistance in the wires would also slightly lower the current. What if you were to do this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Our ideal model would instantly be fully charged since there is theoretically no resistance to limit the current from the battery to the capacitor. In real life, however, as we mentioned earlier, the batteries and the wires would have slight resistance, and the capacitor would take a little more time to fully charge.